we've been talking about the Hodgkin-Huxley model of the squid giant axon. This model, and in fact all conductance-based neuron models, are nonlinear systems of differential equations. This means that we can only solve them using numerical methods, and in this video I will show you how to do this using the exponential Euler method for conductance-based models. And I've already talked about this method in a previous video for passive neural membranes, and it can be easily extended to the Hodgkin-Huxley model and other conductance-based models. The basic idea behind the exponential integrator method is to express the differential equation in the following form. Here, x is the variable that's changing over time, xss is the steady state that value will approach, and tau is the time constant. Now, if the steady state and time constant are both not changing over time, then this would be a linear differential equation, and we can provide a direct analytical solution for x. In fact, one of my earlier videos shows how this can be done for the passive neuronal membrane. However, unlike the passive neuronal membrane, conductance-based neuron models, such as the Hodgkin-Huxley model, are nonlinear, and thus we can only numerically solve for their solution. So how do we do this? Well, what we do is we consider small steps in time, delta t. If this time step is small enough, the steady state and time constant for our variable x here will be approximately constant. So thus we compute an estimate for x within a small time window in the near future, and then recalculate our estimate of xss and tau and continue. So I've written how this is done in two different notations here. I think this is the notation I mentioned previously when we talked about numerically solving for a passive neuronal membrane with a noisy current input. This is perhaps a more verbose way of saying the same thing. Essentially, we're looking at a particular point in time, t0, so this is the current time or the current state of the system. And what we want to know is what x will be at some point in the future, t0 plus delta t. And I've already derived in a previous video that this is equal to the steady state of what x is, and we calculate that steady state at the current time, t0. And remember that xss is changing over time, so we have to just look at a single snapshot, so to speak, in time. So it's equal to the steady state minus this exponential decay term here. And this is just a different way that I wrote this. Here I'm talking x of n plus 1 is x at the next time step, and x of n is our current x. So now I want to talk about how to apply this exponential integrator technique to conductance-based models, or the Hodgkin-Huxley model. So what we want to do is we want to find a way of expressing our membrane potential differential equation in this form, where the voltage is approaching some steady state and has some time constant. That's going to be what's mostly new in this video, so I'm going to put that off for a second. The other kinds of differential equations in the conductance-based model are gating variables, such as the activation and inactivation variables. And interestingly enough, we have already covered how to express these equations in this form. I've already explained that you can model switching between open and closed states through this kinetic model, and typically the alpha rate, or the rate of opening, is voltage dependent, as is the rate of closing. So that's where the voltage dependence of the model comes into. And we've explained that the steady state is equal to alpha over alpha plus beta, and the time constant is just 1 over alpha plus beta. And I've derived all of this in. And Gi is 1 over the resistance, so that's the conductance, and this is the driving force here. So this is just Ohm's law in a different way. And in case you're wondering how this relates to the Hodgkin-Huxley model, as I've explained it, I've made the substitution that Gi equals the maximal conductance of the ith current times MI HI. So, and these are typically to some exponents P and Q. So the point is that this is the maximal conductance, which is just a constant term, scaled by the number or the proportion of open gates. So this is the total conductance if all gates are open. So if all gates are open, that's the total conductance, and this is the proportion of open gates, or of open channels. Okay, so that's what this equation is, and in the Hodgkin-Huxley equation there's only two conductances, a sodium and a potassium, but in future videos we'll be talking about models with many other conductances such as chloride, potassium, or other potassium channels and calcium channels. Okay, so this is the membrane equation. This is how voltage changes over time in a generic conductance-based model. Well, what I'm going to do is first multiply this negative into each term in this sum, and I'm also going to distribute this GI into this term here. So once we do that, we have C dV dt equals the sum. I'm going to drop the I in the sum because there's only one sum anyway. Now we have GI EI minus a second sum GI times V. And now I'm going to factor out this V here because this V is the same in all the terms on this rightmost sum. So then we have C dV dt equals the same thing here, GI EI minus V times the sum of all GI. And the sum of all GI, this is the total conductance of the membrane, or 1 over the membrane resistance. Okay, now you can see that we're sort of inching closer, right? Because now we have the voltage in this term, so what we want is VSS minus V. So we have minus V, but we have this other unwanted factor here, which is the total membrane conductance. So what I'm going to do is divide both sides by the total membrane conductance. So then we'll have the, that was C over the total conductance times dV dt. And here we'll have the sum of GI EI over the sum of GI minus V. And now we are essentially done. I'm going to call this here tau V. And I'm going to call this here VSS. And then we can write our final form, VSS minus V over tau V.